everybody to be connected. Good afternoon to most of you. Good morning to some Americans who have joined us this morning for this very nice webinar. I'm really glad to be here today with all of you. We are here today to discuss about microprocessing with femtosecond lasers using beam shaping based on our MPLC technology and our CANUNDA-PULSE module, which was tested with our partners from LASEA to manufacture microfluidic chip. So today they're going to be me. My name is Gwenn Pallier. I'm product line manager at Cailabs. I will be with Julien.
Hello Gwen and Mark. Hello everybody. Thanks for being here. My name is Julien Bayol. I'm working at Cailabs as an assistant product manager.
And we are with Mark from LASEA.
Hello everybody. I'm Marc Desculteaux from LASEA and engineer from the R&D department.
Okay, so we will have a short presentation. I just want to start by saying that we have Tatiana, who is with us on the backstage, handling whatever technical issue that we would have. Don't hesitate to write in the chat if you have any question, any issue or whatever. She will be answering. And you can use the chat as well to ask all the questions that you have. We will have a Q&A session at the end of the webinar. So today we will discuss microprocessing and the challenges of microprocessing. We will start by explaining what are the exact challenges that we want to address with our modules. That will be Julien presenting this part. I will be explaining then the solution that we have provided for beam shaping for this very specific process. And Mark will be then explaining all the results, all the process results that we have had with our module, and we will have a short conclusion. So I leave the floor to Julien to start.
Thank you, Gwen. So before we go more in detail in this presentation, I suggest that I make a short presentation of our company, Cailabs, which is a French deep tech company specializing in developing, manufacturing, and the selling of innovative optical components, more specifically in the beam shaping field. So our activity is based on the exploitation of a unique technology, the MPLC, for multiplane light conversion, and thanks to our expertise in beam shaping. This technology is actually patented, and we have actually filed 19 patent families today. All of this is possible thanks to the collaboration between more than 60 employees, including 20 PhDs. And also thanks to the almost 17 million euros that has been raised since the funding of the company. About our business activity, it is based at 70% at the export, and we have more than 20 sales partners around the world. A few words about our technology, the multiplane light conversion, which is a technology for beam shaping. It consists of a succession of spatial phase profiles with a specific propagation distance between them. This technology is passive with no intrinsic loss. So as you can see on the left pictures, the very first original implementation was transmissive, but currently in our beam shaping module, it is implemented in a reflective way. That means that the light is go back and forward into a cavity composed of two mirrors, one being textured. This reflective implementation is useful because we can handle high power and high energy lasers. Also, multiple beams in the output and input can be shaped simultaneously. All those characteristics make the MPLC a good candidate for high power and high energy shaping and combining. So thanks to this technology, we can address various applications. So in addition to developing of tailored optical solutions through custom projects, our activity is divided in 4 product lines. The first one is Aruna, which aims at boosting the speed of fiber infrastructure of local networks. The second one is Proteus, that is dedicated to laboratory research. The one other is Tilba, that is ensuring the reliability of laser communication. And last but not least, we have Canunda, which is the product line that we are going to talk today, which aims at improving laser material processing. So this product line is composed of 4 references. The first one is CANUNDA HP, which is a beam shaping solution dedicated to high-power CW lasers. And the 3 other references are dedicated to pulse laser. The first one, CANUNDA-PULSE, generates high-quality bezel beams. We also have CANUNDA Split for beam splitting of pulse lasers. And to finish, we also have CANUNDA-PULSE, which is a beam shaping module for ultra-short pulse lasers. So that leads us to our first part of this presentation. What are the challenges of USP, ultra-short pulse laser processing? So I think it's interesting to remind why it is interesting to use USP lasers for material processing. So we call USP laser when the pulse duration is in the range of the femtosecond. And the main advantage of this laser over CW lasers is the fact that there is no, it is an athermic process and there is no heat affected zone. Also, when we compare it to nanosecond pulse lasers, there is no or less shock waves. All those characteristics make those USP lasers very interesting because they show higher quality and higher reproducibility when we compare to other lasers. And this is particularly true when we talk about microprocessing. So microprocessing is concerning a wide range of processable materials such as metals, ceramics, semiconductors, polymers, or organic materials for a wide range of applications such as engraving, cutting, drilling, welding, surface texturing, and thin film removal. And these microprocessing applications are used in various industries such as medical devices, watch industry, automotive and aerospace, glass industry, or electronic industry. So if I would say what is the biggest challenge to take up in USP laser processing, I would say is to increase the yield while maintaining a high quality process. So if you want to increase the yield of your process, you have basically 3 solutions. First, you will have to increase the energy or the power of the laser, but this has an upper limit, which is the damage threshold of the material that you are processing. Also, in parallel, you will have to increase the scanning speed, but this time you could be limited by the hardware, meaning that the scanner. And to finish, you can split your beam in order to parallelize your process, or also shape it in order to optimize the energy deposition on your material. This leads us to a very complex trade-off in between 4 main functions. At the first, you have to stabilize your laser beam if you want to be able to shape it or split it. Sorry, and also your technology has to be able to allow sufficient cooling when you increase the laser power and energy. So this very generic challenge is also applicable when we talk about our specific problematic, which is the microfluidic chip manufacturing using an USP laser. So first, what exactly is a microfluidic chip? This is the compilation of diverse laboratory operations, such as blood or DNA analysis, or for example, PCR tests, which unfortunately are well known today. All of them concentrated in a chip with micrometric dimensions. Micrometric dimensions means that the channels into this chip are in the order of the micrometer. The chip is not bigger than your credit card. So how can we manufacture this chip? First, you have to engrave the channels into a polymer material. For that, it exists different methods: injection molding, lithography, or again laser. Laser is very interesting for this step of manufacturing because of its flexibility, and you will be able to generate and to produce easily good quality prototypes. Then you have to seal the 2 parts, the engraved plate and another plate of polymer material. And for that, you also have conventional techniques such as thermal bonding or ultrasound welding. You can also use a CW laser or, of course, an USP laser. And this is actually what we are going to talk today. And this is the aim of the collaboration between Cailabs and LASEA. So the objective is to increase the yield of the microfluidic chip welding using an USP laser while keeping a good quality. Okay, so before I leave the floor to Gwen, I suggest that we do a little and quick survey session. So for that, we will ask you a question, which is the following: what techniques have you already used to improve your laser processing yield? For that, I invite you to answer to this question. Maybe you already have tried beam shaping, or maybe beam splitting, fast scanning hardware, or maybe you've tried to only increase the laser power. Maybe you've tried another technique, which is not displayed here, or maybe none of them. So I invite you to vote. I think that some of you didn't vote yet, so maybe we will wait a few seconds more. Okay, 69% of you. Okay, few seconds more. Okay, so I think that that's it for the results. So as we can see, some of you have tried first fast scanning and increase the power, which is, let's say, the conventional techniques. Many of you also, about 38%, have tried beam shaping. So those results are very interesting, because we see that actually the solution to improve the yield of your process may be actually a combination of all of those techniques. And this is actually what we are going to see today. In the next section, we will show that combining beam shaping using a CANUNDA-PULSE module with a scanner have increased the speed of the welding process by a factor 7. And so for that, I will leave the floor to my colleague Gwen for the second part of this presentation.
Thank you very much, Julien. So it's very good. We managed to do the survey. We are not lost in our slides. It's perfect. Great. So let's carry on now with the presentation of the optical results. So as Julien did just say, we at Cailabs, we are focused on trying to provide beam shapes that are optimal for different processes, multiple processes, as Julien did explain. But we will focus today on these microfluidic chips. So basically, for USP processes, what we try to do is basically either having the optimal shape with a single shape being a square or round, or having multiple splitted shapes. Actually, all of this has been tested with LASEA already in the past, but we will focus today on the so-called top-hat shapes, or the tailored top-hat shapes. So how does that work? I think it's a good start to explain basically how our module is actually installed and used inside one of the LASEA machine. The idea is actually that you have a laser. In this case, it's a laser from Amplitude, femtosecond laser delivering 100 microjoule per pulse at 1 micron. Then you have actually an injection telescope. It's a telescope that is made to adapt the beam waist to the proper dimension inside our CANUNDA-PULSE module. After that, you have our module, which is delivering a round shape of 600 micrometer diameter. It's going through an LS scan from LASEA, and it's going through a 100 millimeter F-theta lens. And you then have in your processing plane a 60 micron diameter round shape. So you can see that it is integrated inside a standard industrial machine from LASEA, and it's actually set with a couple of mirrors in between the injection telescope and the CANUNDA-PULSE module in order to tune the alignment of the beam compared to the module, the shift and the tilt of the input beam. So in order to calculate quickly the appropriate injection telescope, LASEA has used their LS Light software. So if you have any question on that, actually, I will let Mark reply later on. But it's a software used to make a quick calculation of Gaussian beam propagation through lenses, for example, and it helped to calculate the right telescope. We will make a stop now on mode cleaning. So as Julien was explaining, when you want to do beam shaping with a monomode laser, you have to really have a stable input. If your input is not stable, your shape will be distorted over time being maybe over an hour, 2 hours. You will have to realign all the time. This is not industrial. And the thing is that femtosecond lasers are very complex to manufacture, and they show all the time some instabilities, even if they are very small. It can be tilt, shift, it can be defocus, ellipticity, or astigmatism. At Cailabs, we have developed a very unique feature based on our multiplane light conversion, which is called mode cleaning, and it's helping the stabilization of the beam after the laser. How does that work? MPLC is based on modes propagation. It means that at Cailabs, when we design our MPLC, we propagate the modes one by one, each mode of the laser. When at Cailabs we see an injected beam which is shifted, what we see is energy inside the main modes, the TEM00, the Gaussian mode. And this energy, we make it follow a specific path and getting out of the module and delivering the proper shaping to the material, to the processing. Whatever energy is inside the tilt, the shift, or other instabilities is considered as higher order modes, and it's following another path through the MPLC. Somehow it's going somewhere else and it's blocked. What does that mean? That means that whatever unstable your beam is, you will always skip the exact shape that you want in your processing plane, and you will have a stable process. The drawback, because we cannot do magic, is that you will lose energy. The more unstable your laser is, the further it is from the perfect Gaussian theoretical beam, the more energy you will use. But doing that, you manage to have the right shape. So what is the right shape? In this case, we have tried something very new. It was the first time that we do some processing using this shape. We didn't really have a name for it, so now we will call it the U shape, because you see it's just like a U. With more energy in the ring at the output of the shape and less energy in the center. So this is really interesting, because when you scan using this shape, you will have a constant energy hitting the material, and this will be described later on by Mark. We were showing a 93% transmission when having a monomode input, so when having a low power monomode input, and we were having very sharp edges. So the way we use to describe the sharpness here at Cailabs is the T/L ratio. We were having a 0.1 T/L. T is the transition length from 90% of the maximum energy to 15% of the maximum energy to the L, the length L, which is the plateau length, the top at plateau length. So it means that actually this beam was 15 times sharper than a standard Gaussian beam. What is important to say when you say that you have a high quality shaping is that you preserve the shape. Having a nice shape just after your module somehow is not very complicated. What is very important is to preserve this shape through the setup, so through the scanner, through the F-theta lens, and over the whole field of view of the F-theta lens. If you are using, for example, diffractive optical elements, DOEs, it's based on diffraction, as the name says. And most of the time, you will have distorted output beams inside the field of view when you are at the edge of the field of view. In our case, as you can see on the left, you have the U shape at the output of the module, and you manage to have the same U shape 10 times smaller in the processing plane. When you want to have also a high quality beam shaping, there is something else which is very important, is phase management. So most of the time, having a nice top hat, a nice shape is possible also in one single plane, but what is very difficult is to preserve it over a certain depth of field. So the reference generally is the Rayleigh range, so ZR, and we will compare it to the Rayleigh range of a Gaussian beam, the equivalent size Gaussian beam, and the radial range of a 30 micron waist Gaussian beam is 2.7 millimeter. And what you can see here is that we managed to preserve this U shape over 1 to 2 millimeter, enabling to have a pretty robust process. So you can see on the left the image when you are far from the best focus plane, and the image of the U shape in the focus plane and how it's behaving through the propagation distance. So now we will try to switch to a video. So give me a second to do that. I will just show you this video. It should be now on your screen. And here you can see actually how the shape is behaving when you are scanning over the propagation. So you have this U shape in the middle of the propagation, and you have a certain depth of field over which you preserve this U shape. And after that, you don't have something which is so weird that you cannot do any process or anything. You have kind of a peak shaped. It's getting again over the depth of field. So you go from the peak shape to the U shape, which is preserved, and then you get back to the peak shape just when you get further from the best focus. Okay, so let me now go back to the presentation. All right. So the depth of field preservation is possible with MPLC because we managed to have the right intensity profile and the right phase profile in the processing plane. And having a plano phase, we managed to preserve the depth of field. So this is really unique to our technology as well. So this is it for the beam shaping capabilities and the optical result. And now we leave the floor to Mark to present the different process results that were obtained at LASEA.
Okay, thank you, Gwen. So I will start my presentation with a little presentation, short presentation of LASEA group. LASEA is a laser integrator, especially for ultra-short pulse laser, but not only. We have 100 employees on 5 sites. We have a lot of patents, represent a lot of continents. And I will show you some pictures of our facilities, especially our new headquarters that you can see here at Liège in Belgium, and with our new hall of production. And now I will speak about our industrial machine dedicated to the microfluidics. We have developed it for the Microlab project with financial support of Walloon region in Belgium. And this machine is dedicated for the microfluidic chip for the engraving and the welding. We are able to make the 2 steps of producting a microfluidic chip with only one tool. For the laser, we'll use infrared laser with ultra-short pulse. We have LS-Scan, the scanner of LASEA. We have also a cobot, a collaborative robot that you can see here. And thanks to it, we are able to make a full automated production. We have, of course, the top hat module from Cailabs, and also a clamping system. Here, it's a patented system of electrostatic charge that will push the film on the chip, as shown in the video that Gwen will show now, please. And the clamping system for, as you will see in the video, we're able to push the film on the chip without any contacts. So here, without any contacts, we will put some electrostatic charge here, and the film will push itself on the chip. And the clamping system is really important for welding, because the quality of your welding will depend directly of the contact between the film and the chip. And thanks to the electrostatic charge, to the electrostatic clamping system, we achieved strong and homogeneous clamping force. And now I will speak about our result. To determine our laser parameters, we use a value that we call the delta Z. We make different lines at different vertical position with moving of the scanner. And we observe for each value if the welding seam is correct or perhaps is too high or too low. And the interval of value for the vertical position where we have a correct welding, we call it the delta Z. And we have made this job. We made this job for a different value of energy deposition. And at the left, you can observe our result with a Gaussian profile. And at the right part of the slide, you can observe our result with a top hat profile. And we see that even with a higher energy per pulse in the case of the top hat profile, we need a lower energy deposition to achieve equivalent results. And what it means? It means that when we could use higher speed to achieve a good quality, a good welding quality with a top hat profile. So our welding is faster with a top hat beam, but also we observe a smaller weld seam. Here you can observe a welding seam with a Gaussian beam, and here welding seam with a top hat beam. Another thing that is interesting, it's the difference of size between the laser line that's directly depending on the spot, the diameter of the spot size, and we have a huge difference of size between the width of the welding seam and the width of the laser line in the case of Gaussian beam. In case of the top hat beam, the widths are already seems equivalent. It's faster and smaller, but also we observe a more aesthetic welding at microscopic scale. As you can observe here, the edge of our welding seam are clearly more irregular in the case of the Gaussian beam than in the case of the top hat beam. And it's really interesting when we're working at the edge of a channel. Here you can observe a welding seam at the edge of microchannel. Here you can observe the microchannel. Here again, and another one here. And we observe we don't have a leak of the sample inside the microchannel because the heating is really local. It's why channels doesn't collapse, and if you have biological materials inside of the microchannel, they will be preserved because the heating is local. The more aesthetic welding aspect is also at microscopic scale. Here you can observe a microchip sealed with a top hat beam and a microchip sealed with a Gaussian beam. It's important to note that here we have it's transparent materials, transparent polymers. So we make weldings of transparent polymers without any absorbent layer. It's the difference between the continuous wave laser technology to seal microfluidic chip. So here we have a good result, as you can see with the top hat beam. The welding have an aspect more clear. And an important thing is the test of hermeticity. And here we will show you a video of test with a complete circuit, microfluidic circuit that we have made. And here again, we will pass on the video. And so here we have a syringe connected to a tube that it's itself connected to a non-leaf connector. and the ink is injected in the microchannels. By changing manually the pressure on the syringe, the fluid in the channel change of direction and of speed. As you can see here, if I change the pressure on the syringe, I can remove or push the fluid inside. And even with this change of pressure, we doesn't observe any leaks in a microchannel. Okay. To conclude my part, we have integrated a new technology in our machine, the technology of Cailabs. And thanks to this new technology, we were able to improve our process. We have a faster process because, as I say before, it's 9 times faster, but thanks to our higher quality of welding, we are able to have a density of welding less important, so less line of welding seam. So, and to seal this microchip, we need less than 20 seconds to seal this microchip. It's really interesting. So we have higher quality for the sealing. And also, we have a smaller weld seam, even if it's not the most impressive results that we achieved thanks to the module. And it's conclude my part.
Thank you very much, Mark. So, yeah, here we are. We will reach now the conclusion of this presentation. Thank you very much again for your presentation and for all those very nice results. So now what is the message that you should be taking home? What is the conclusion of this presentation? Well, from the Cailabs point of view, we have provided a high quality beam shaper. This is based on multiplane light conversion technology. This shaper was providing a sharp U profile, 15 times sharper compared to a Gaussian beam. The shape was actually tailored in order to be the optimal energy deposition for this process from LASEA, and the shaper was compatible with the industrial machine used for femtosecond processes. From the LASEA point of view, as Mark did just say, well, they have managed to improve the yield of the process. It was 9 times faster compared to welding with Gaussian beams, and the quality was improved as well. I want to conclude by saying that we have this very nice collaboration with LASEA for 2 years now. They have tried some of our modules, always getting very nice results. The next one coming is will be detailed and released at Cailabs. So Cailabs is 3 weeks from now. So follow us until Cailabs, and you will see the result that we have doing beam splitting with green femtosecond lasers. And that's going to be nice as well, not with Mark, but with someone else from LASEA, actually. So we will now reach the Q&A session. So don't hesitate to ask all the questions you have in the chat. Even now that the Q&A session has started, you still can ask your questions, and we will go to the Q&A. And I should be able to now show the questions. Give me a second. Here it is. So I will read all the questions, and I will then let either myself, Julien, or Mark answering the questions. But I think most of them are actually for you, Mark. So Mark, get ready for answering. So to LASEA, do you have to control humidity in order to assure your static charge camping system work properly?
No, we don't control humidity. No, we don't need. Perhaps for other polymers, or for example, if we want to work with glass, perhaps we need. But for right now, we don't. We never have need for that. It's working well with this kind of polymer.
Thank you. So another one for you. What is the diameter of the microchannel roughly?
We're working with microchannel of 100 micrometer or 200 micrometer. I don't remember exactly the size of the microchannel that was in the presentation. I think it was 100 micrometers of diameter.
Thank you, Mark. Another one for you. So you showed results with round top hat. Would there be an interest to have other shapes that could be delivered by Cailabs product? So this one is from Fabien Guez, who Julien and I know very well. He's from Cailabs, actually. Thank you.
I don't know. Perhaps we have to test. Actually, I don't have any idea. Perhaps it could be interesting.
Okay, it was for you, for LASEA, so I let you answer, but I know that we have other things together, but some of them are confidential for now because it's for specific projects, European funded, I have in mind, for example. But there are other shapes interesting, and hopefully we will describe that in a future webinar in some months or years. All right, so another one for you. The color is from process, or you can keep the channel transparent.
Okay, the problem of the color with it's due to a bad quality of engraving with a top hat beam. We have a better result with a Gaussian beam, but for it was easier to make the engraving with a top hat beam on the same on the machine. But if we work with Gaussian beam, we'll be able to have a better result on the color and on the roughness. The best roughness that we have achieved was 100 nanometer on the COP.
Okay. Curiosity question on how you align the microfluidic channels with welding trajectories.
We using camera, a special camera for recognition of form, and so between the engraving and the welding, we make a new alignment thanks to the recognition form camera.
Okay, at least we have one for us. You can relax a bit, Mark. So for Cailabs, do you think it would be possible to inject the shaped beam inside a higher harmonic generation module to obtain, for example, a top hat green beam? It's a very good question. Actually, how to get a nice green top hat is a question that, of course, we have asked to ourselves. I believe still the easiest is actually to do the frequency conversion first and shape it after. We have actually results recently. For now, we consider it as R&D result, meaning that it's not yet a standard product, but it will become very soon because the results were very good. It is possible to actually shape the beam with green input, actually, and it sounds simpler since the frequency conversion is done just after the laser most of the time. So another one for you, Mark, again. Do you have experience with glass? Well, that's a very broad question.
Yes, we have experience with glass. We are able to make welding and engraving with glass. I don't remember exactly the results, so I prefer to not say any mistakes. Say any mistakes here, but don't hesitate to contact me. I will be able to give you more details about our experience with glass for welding and engraving.
Okay, so another one. What will be the depth of focus? Whether the depth groove will have uniform width throughout the groove? I don't know if it's for you, for us. At least for the depth of focus, I can reply. Basically, we try to reach the radar range in terms of depth of focus. We cannot reach it exactly, but in this case, it was like maybe 50% of the radar range. It depends somehow on the shape. Sometimes we manage to reach up to 80% of the radar range for some smoother shapes. For the depth of groove, then I leave it to you, Mark, to answer.
Yes, it's when we make our micro channel with a Gaussian beam, we don't have a really slope edge. We still have a little, we have a little slope, But the width is uniform at the bottom of the groove. Yes, we have clearly a smaller spot size than the size of the micro channel. So yeah, we're able to have a uniform width. It's depending on what tolerance you're speaking.
Okay, another one. Is there any in-process monitoring during welding, or the images are post-welding?
It's post-welding.
All right, so I know I will see if there are other ones which were not considered as questions in the chat. I think there we have missed one. Let me. Okay, so the last one. During welding, could any top-at beam degradation be expected when the beam passes through the polymer sheet on the top of the microfluidic channels? Okay, one.
Yes, perhaps because you have the polymer. It's an optical surface, but we don't have analyzed that. It's difficult to respond to this question. We don't have make an analysis about that.
Okay. I guess if any of you want to have more information on that, you may contact any of the three of us, and you will reach us through our email that you can see here on the last slide of our presentation. I want to thank you all for attending this webinar, and a special thank you, of course, to Julien and Marc for presenting it with me today. And I want to wish to you all a nice day or a nice evening, and we remain at your disposal if you have any additional question.
Thank you, Gwenn and Marc. Bye. Thank you all.
Bye.